Hi everyone, thank you for coming for my talk. I want to start today with a funny story. So actually I almost didn't make it here. I flew with an airplane company that's not that good, and I don't want to name names. Let's call them Schmunited. I didn't say that. It's called Schmunited, and they canceled my 2 flights here. They lost my luggage. They delayed my flight 23 hours. I'm here. But I think I'm suspecting they really hate metaprogramming. They didn't want me to come here and to teach you about those things. So blame them. Oh, well, I didn't have another choice. So that's it. Okay, a few words about myself. I'm Dathskovsky. I have started a new site where I'm posting blogs about C++. I have posting weekly posts about C++ and things, interesting things in the modern world of C++ on LinkedIn, so you can follow me there. And I work in an exciting company from Israel. It's called speeddata.io, where we are developing the next big thing in big data. It's going to be something that accelerates big data analytics in a rate of X100. You can watch one of my talks from CppCon about what we are doing and CPU architecture, but it's not what we're going to talk about today. So let's start. What do you think? The first thing that comes to your mind when you hear the word templates, the scary boogeyman monster for everyone? Anyone wants to answer? Yeah. Handle brackets, that's it. Handle brackets. Something else. So you're in the correct place, from what I understand. No one is afraid of templates. But most of the people go to shock and panic when they see this. When they see something in your code base with this brackets, they go into shock. There's another funny story. My previous job was at Abbott, and I have developed something. A pluggable system that was very templated. It worked wonderfully, but when people saw it and they had a bug in it, they would just come to me and say, that's your problem, I'm not touching it with a stick. So what I'm trying to say is, it's not such a scary boogeyman thing that most of people think it is. And I hope after this talk, you will see it as well. It's really beautiful, the things that you can do with it. And with C++20, it even got better. Usually I start with some kind of rules for templates just to make it a smoother transition to what we're going to do here, but I don't have time for this in here. And we're going to drive right into what we're going to do here. We're going to develop a concept that detects containers. We're going to see how it was done with C++ 11, 14, 17, and then we will go to concept in C++20, and we will see how it makes things much, much better, cleaner, and maybe most of the people will use them right now. We will start with the trait library. So trait library was introduced in C++ 11. Who uses it? Wonderful. 2, 3 people. Wow. 4, 5. 5 people from all the crowd uses it here. It's amazing. It's basically, you can use this thing to query your types. You can ask your type, what are you? Are you a pointer? Are you an abstract type? Do you do something like, is it the same type as T and U? And it will answer you. It has value, it has types inside it. And it's really, really made our lives in C++ 11 better for people that do use templates a lot. It became easier to do those things. So what do you do with those things? You constrain. You constrain functions, you constrain types. You do the things that you used to do it with regular templates, and you have to implement everything by yourself, but now you have the standard library. Let's look at this example. So who here knows FMT library? Who uses FMT library? 2 people, 3 people know about it, 2 people use it. Great library. Before C++20, before C++23, we didn't have the print function that we will get soon. And actually, until this year, we didn't have the stud format. So FMT does everything for you, and it does it in a very great way. I hope that the compilers will take it faster and actually get to where they need to be. But this library is just something that formats strings for you and prints them out if you need it. And it's really easy to use it. It does some things in compile time. It's really friendly, and you can do everything with it. So this function is just a templated function that receives any type and needs to print it. What do you think? Is it okay to use it like that? No answers. So no, it's not okay. Why is it okay? Because the FMT library has a problem printing pointers that are not void. They cannot format it just like that. I could do it with another example, but this is a nice example just because FMT library is so friendly. It will tell you what the problem is. So here it says, okay, you're trying to print something that is not void pointer. I don't know how to do it. Please explain or create a new sync to do that for you. How can we fix that? There are many ways to fix that, but we will talk about few of those ways and how I approach things. So the first way that we will do it, is with helper structs. Here we are creating two structs. One of these structs is templated on a type and a non-type template parameter of type bool, and it has a static function in it called print. This function receives the t parameter that we are providing, and it is printing something. It's printing everything that is not a pointer. The other struct is a specialization of the first template struct, and it has the same print function, but now we know that it's a pointer, and then we're just dereferencing it because we know it's a pointer. The last thing that we need to do is to create another function, our main print function, that receives a template and prints it. But the second parameter, it actually calls the struct. It says, okay, I'm working with the type T, and I'm using a trait that's saying, is it a pointer? And then take it a value from the pointer and instantiating the function from inside the correct class or struct. And yes, I have discarded the void pointer. It's just a toy example. We just need to understand that it's there. Another way that made our life a little bit cleaner and easier is the trait library. It added _t and _v in C++17. _t was added in C++14. So basically, _t is just taking the inner type from the trait. Instead of writing all those brackets and points and everything, you just do _t and that's it. And _v is taking the inner value from inside the trait. It works like that. And that's how it makes it a little bit cleaner. So this is the same structs from before, but right now we're using isPointerV, and we don't need to do all the brackets. It's a little bit cleaner, it's a little bit nicer, but it's almost the same. Another way to approach this problem is not creating structs at all, and it's using overload resolution. Why can we use overload resolution here? Because the type traits themselves, they hold a type. The type inside the type trait is a false type or a true type. False type or true type are basically strong types for false and true. And that's why we can overload from them. So the first function is templated on T, and it receives a false type, and then the value that we want to print. The second function is templated on T as well. It receives true type, and then the parameter that we want to print. If it's a true type, then we know it's a pointer, and we need to dereference it. And then we need to create the third function that receives the parameter, that calls the other function that is overloaded with as stud isPointerT, and taking the type, instantiating it, providing it to the function, and of course giving it the actual parameter that we want to print. In my opinion, it's a little bit cleaner because you don't need to use all those hoops with structs and static things. You're just using regular functions. And another just thing that it's worth mentioning, the type name on line 18 If you're using Clang 16, it's gone. You don't need to use it anymore. This is the way that we will implement it with C++17. In C++17, we got something really nice that made metaprogramming easier. It's if const expression. If const expression is basically saying, if I'm taking one branch from this if, the other branch will be removed during compile time. So it won't compile it at all. So if it's a pointer, it will compile just one part of the function. If it's not a pointer, it compiles the other part of the function. Basically, there are two different functions there, and it will select the right thing for it to do. That's C++17. With C++20, we can do even better and cleaner. We can just create two small functions with auto. Auto is the weakest concept of them all. Auto says, accept everything. But the problem here is that we lose the constness. We lose the constness because const auto reference may receive a pointer. So it will not work. And we lost it here. I will talk about how to fix it. If you want to know more about it, you can go to my blogs in LinkedIn, and I wrote an article about that. But basically, in C++20, you can just add the constness like that. You have const autoreference, and we have created some concept that's called pointer that says only pointers may enter here, nothing else. And then you just write const pointer autoreference, and it will receive only pointers, and then it works. In my opinion, this overload resolution is the best way to go. It's cleaner, it's more modular, but it's up to you. As everything in C++, you have many ways to do those things. Sorry? Pointer is not a keyword. It's a concept that I created for this. So this concept says the parameter that is received by the auto has to be a pointer. As I mentioned, you can go to LinkedIn or to my C++ Now talk about the same issue. And I'm talking about the pointer concept in more details there and why is it a problem, why we cannot use const there. Container detection. Let's get to the main event here. So now we will detect a container. How we will detect a container? So the most naive way to do it is to say, all containers in the standard library has iterators. So let's take it for our advantage. But before we get there, we need to learn about more tools for metaprogramming. So one of the most important tools for metaprogramming is Sfine. Sfine is a very funny name to say that if you have something that can substitute an error, that's not an error. Just substitute it and die quietly. Just let the program continue compiling like never happened. Another very important rule that goes hand by hand with Sfine is ellipsis. Ellipsis functions, the 3 dots ellipsis functions, are inferior to any other function. So you can always use it to your advantage. In this example, we have the print function, one with ellipsis and one with an integer. And then we are calling a function print with 17, which is an integer. And the compiler will always want to call the most concrete function. So it finds the function on line 10, and it calls 17. We don't have a concrete function for strings, so it will call the ellipsis function. And you will get integer and ellipsis. And this is the basic and the most naive way to detect a container. We have a templated class. This is a trait. We have a templated trait on T. Inside it, we have 2 functions. One is with ellipsis, and one is without ellipsis. With S iterator, if the type that the function is templated on has an iterator inside it, it will be able to use it. If not, that's Sfine for you. And because we have the ellipsis in the other function, all other types can just be replaced, and just no error will happen there. Another thing, in line 14, we have the value itself. If you can see in line 9 and in line 12, in line 9 we're returning byte. In line 12, we're returning size t. That's important for us to get a value. So we know that if a type has an iterator, the function that will return the size t will be used. So we are saying here, we will activate the function from t that was templated on the class. We will provide 0 to it. 0 is null pointer, or 0. And we will compare it with the size of t. So it will be false if it's not a container, and it will be true if it's a container. An idea for usage, it's a kind of pop quiz here. Will this work? The answer is no. It cannot work without const expression because a type cannot be iteratable and not iteratable at the same time. And if it doesn't have const expression in it, it will try to compile everything as one block, and then it will just fail. So what can we do about it? We already talked about many things that we can do. We can delegate to a helper class. We can delegate to a helper method. In some cases, we just want to overload it, but we can use all those methods, but not the C++17 one. More tools that we need to know before we go from naive to actual container detection. Very important tool that people don't like in C++ is EnableIf. EnableIf is basically a very neat way to make the compiler select the right thing for you, what you want it to do. It enforces the compiler to use Sfine. So you may do something that enforces the compiler to use exactly the function that you want from a Boolean expression. And if you can, as you can see here, the implementation is really similar to the class that I have presented before. There's nothing new here. And that's how we will use it. So we have the print functions that we like. Both of the functions are just templated. Both of the functions receiving the t parameter as the parameter that we want to print. The first function uses EnableIf t and says, if it's not a container, the type that I will provide from inside it, it's void pointer, and it will be null PTR. In this case, I know it's not a container, and I'm just printing a regular value. On the other hand, I have the second function, and here I'm using EnableIf t, and saying, is it a container? If it is a container, I'm providing a type out, which is void pointer. It's still null pointer. We don't care about the value there. And it will print it as an iteratable values. So if we will use print with 18 and print with std array 1 to 3, we will get 18 and 1 to 3 accordingly to the functions. And one of the functions will always be hidden because of Sfine here. This is the C++17 usage again. Here we have const expression if that asks if this is a container type, then print it, if it's not a container type, then print it as a non-container thing. If it is a container, go and print a container and print all the values from inside it. And it works. We have a number 2 and container 1, 2, 3. Another important tool is Voity. So EnableIf works on one thing. It has a Boolean expression inside it. And if the Boolean expression is true, then it will give you a type and a type from it. If the Boolean expression is false, it will give you nothing. And that is why Sfine happens. Voity works on multiple types. So it's a very simple alias for saying, if all the types inside my template are well-formed, then void t is a well-formed void. And that's how it's implemented. We don't care about the types. They just need to be well-formed, and then it's a void. That's it. And thanks to Walter E. Brown, we have it since C++17, and we don't have to implement it by ourselves, even though it's super easy to implement. But if you already have it, let's use it. And now let's get to the actual non-trivial way to detect a container. So all containers in STL bind to those 6 rules. Each one has begin iterator, end iterator. Begin and end iterator can be non-equal comparable. Stud next can be invoked on std begin. Begin iterator has the reference operator, which returns something that is not void. And begin iterator and tell iterator are copy constructible and destructible. So if you have 6 of those rules, you're certain that the type that you are looking at is an actual container in C++. Let's begin the implementation. We have to know that the type is actually, it has a begin. So we need to use decal type on stud begin on decal val of the templated parameter. Already looks wonderful, right? Same thing for t-end. We need to know that we have a type that can be derived from stud end and using decal val on C. Who knows what decal val is and what it is used for?
It constructs the object without actually treating the object.
It's not comparing the object, it's creating an object without a constructor. So it's an instantiation that is not valid, but it's good enough for doing things with templates and detecting types. If you will use it in an invocable location, it will not compile. And in lines 72 and 73, we have not equal. So we need to do decal type on stud decal val for BI and not equal stud decal val on AI. It should return something, and this is the type that we will use here. Incrementable is almost the same thing, always using decal value, using stud next instead of stud begin, and decal type. Then we have a decal val for dereferenceable. We need to know which type we are receiving if we are dereferencing BI. And this is the simplest part of detecting a container, the base class template. So we have template on C and a type name that is void. We don't care about it. Struct is container, and we are inheriting from false type. So that means if we will get to this struct, this instantiation of this struct, that means that it's not a container. But that's how you implement the actual type trait. So we are templating, it's a specialization on type name C. We have a struct that is called isContainer with C, and then inside the second parameter, we have stud void T on T begin, T end, T increasable, T not equable, T derefable. That's it. All these types need to be well-defined types. Only then void T will be well-defined. If it will not be well-defined, the previous implementation will be called. And we are inheriting from std stud integral constant. Integral constant is just constant thing that you want to create. It will be integral constant of bool. And our integral Boolean expression is if it is convertible, not equal T begin and T end. If it's convertible to bool and not is void T dereferenceable T begin and is destructible T begin and is copy constructible T begin and is destructible T end and is constructible T end. Wonderful. This is the usage. After writing all that amazing templates there, the usage is pretty simple. You need to use it. You can use it from a function. You can take the value from it because its constant value has it. A false type has a value inside it, so it's usable either way. You can use it with EnableIf. So get first parameter, you are creating EnableIf. You are saying if it is a container, then this function will be instantiated, then it will be called, and then we know that it's a container. Container has a begin and dereferenceable, and it will return something. And in the second example, get first two, it's almost the same thing, but instead of using the EnableIf on the return type, we're using the EnableIf on the template itself. Any problems, anyone? Is it code that you would actually implement? I see people laughing, so I guess not. So yeah, that's a lot of code that only template experts would write. And from my experience, I write a lot of templates. It's horrible to debug those things. It was horrible to debug those things in the past. It's easier now because the newer compilers, and when I say newer compilers, it's Clang 12 and higher, and GCC 10 and higher. The error messaging is a little bit better, but still it's horrible. To debug things in compile time, you need to understand what you're doing. And to write those things correctly, you need to understand what you're doing. And basically, most people, when they will see this code and someone will tell them, go maintain it or do something in it, we have an error, that's just a headache. Now we're getting to the fun part. C++20, how can it help us with writing the same thing? How will it look in C++20? We already saw that we have a concept called auto and how it works, but it's much more than that. Just like with C++11, where we got the type trait library, here we have the standard concept library. So already out of the box, you have many concepts from standard that you can use. For example, you have same as. Same as is almost the same as is same, but it's not a trait, it's a concept. We will get to it, but you already can use many, many, many things on your code, and it's simpler. We will see it in a moment. So here's an example of an usage. We already saw the auto pattern, right? It's the weakest concept of them all. And all this function does, the full function, is just comparing A to B. If you will use it like that, that will be deduced to int, and that's right? No problem here. We're just comparing int to int, and that will be fine. If you will use it like that, int and double, it still be fine. It will be compiled. Double can be converted to an integer when we implicitly convert it to an integer when we're doing the operator equals. But probably it's not what you intended to do. The auto is very forgiving. But if you will use it like that, with one, which is an integer, and stud vector of ints, it will not compile. But it will not compile only because when you're trying to use the operator equal. Because the standard says, I don't have an operator equal for integer and vector, but still the function tries to be compiled. It's not constrained. It's not really constrained. How can we fix it? You remember the pointer thing that I talked about? So we have a lot of things like that in the library. Pointer is not something that's implemented in the library itself, but we have integral. Integral means I want you to receive only integral types from this auto. And as you can see, I don't write the brackets here because that's one of the things that are really nice about concepts. The first template type to a concept is deduced from the parameter that is used upon. So if A will be something, the stud integral will take the type and deduce whatever it needs to be, that needs to be done inside the concept itself. So if we will use it like this, 1 and 1, it's still okay. There's no problem here because it's int and int. But if we will use 1 and 1, 0 in this case, this will not work. It will not compile, and it will tell you double does not satisfy integral. Easy as that. You understand when you write something wrong, it tells you what you did wrong, without going around a lot and like you have you're missing a semicolon on line 24 and then you go to line 24 and it blows in your face. We can constrain not only parameters to function, we can actually constrain variables. So here you can see an example for a variable, an auto variable that you can just write inside your code. And we want that val I will be only integral types. And when it receives one UL, it works. We want to, the other one, the val f, it's only a floating point type. So one point f, it's a floating point, it works. If we will try to do something like that, floating point for val f2, and we will try to assign it with val I, which is unsigned integral type, it will not compile. It will just say unsigned long does not satisfy floating point. Yes? It will not allow it. Look at it. That's exactly the example. So you're saying floating point. You want a floating point. You don't want it to be converted to integral. I want it to be just floating point. And we are trying to give it integral, and it says no, unsigned long cannot be a floating point type. Not only we have a lot of good concepts already under our tool belt, and we can use them without doing anything, it's really easy with C++20 to implement your own concepts. So it's easy like that. This is called the name concept that uses a clause, a require clause. We will get to it very soon. But here you can see that it's just a template. You're saying it's a concept. The concept name is convertible to int. It's using a concept from the library that we are providing t to the concept and int. And this concept will be always true if the type that we are providing can be converted to integer. We can create it with conjunctions. So here we want something to be convertible to integer and not to be double. So we're using our convertible to int from before, and we're saying not, and not, stood same as t double. That's pretty understandable. When people will try to read this code, they can understand what it says and what you actually want from them. We can use this junction. So if we want something that is int or larger, we will use same as int, or size of t that it was provided is larger than the size of int. Easy as that, or and disjunction conjunction, everything works. The third thing you can do is use atomic concepts. So atomic concepts are atomic expressions, but the thing here, those atomic expressions have to be Boolean. Implicit conversion is not allowed. So if you are doing something that is atomic, it has to be a Boolean. Here I'm creating a type, call it SC, it's a templated type. If it's not been templated, if it's a bool thing, then it will return false. If it's something else altogether, it will return true. And the concept itself, it's atomic concept that I'm saying, okay, I will create the struct itself SC on the type that was provided. I will instantiate it and call the function. If it returns true, it's true. If it returns false, it's false. It's an atomic concept. Require clause. Another way to do things with concepts is not to define the name concept. Sometimes you want to do something quickly. I really don't like this, but as everything in C++, you have many ways to do things. So here we are saying it's a trailing require clause on the template type itself. We just need to write template type name t, requires size of t larger than size of int. And this struct will be instantiated if and only if the type that is provided to it is larger than int. Another way to do things is require expression. So require expression is the most important thing in my opinion because you can do most of the things with it. This is a name concept that receives two things, bi and ei, and we are saying this concept is called not equal on. It requires, require expression is like a function. So you need to say requires, it receives parameters of type bi and ei, so you will never need to write decal type again, decal type, decal val, all those wonderful things. Just receive those parameters. The compiler will create them for you. And then inside here, I have written something that's called compound expression that says that if bi not equal to ei, if it's possible, and it returns something that is convertible to bool, then this will be satisfied. If not, this will not be satisfied.
So can you give an example that for that one? Like if one of them is integer and the other one is double floats, then
that's fine. That will be fine, and it will be convertible to bool because it returns bool. But if it's going to be, for example, something like integer and vector, you cannot instantiate not equal on an integer and vector, so it won't even go to is it convertible to bool because it doesn't have a return type. Here's an example. So require expressions are wonderful. Wonderful to use. You can do a lot of things with them, but there are rules. Here I'm creating my same as. And I create it with a require expression. I want to receive two types, T and U, to the require expression. And I'm just invoking stud same as T and U. So it should be okay. Then we are using a function, do only on same, and we're saying, okay, X can be anything you want, X can be anything you want. My same as decal type of X out of Y. That means I want Y to be of the same type as X is. If not, please don't compile. But just to be sure, I've added this static assert inside here that's saying if those types are not the same, please fail. What do you think will happen here? Where would we fail? The constraint or the static assert? Oh, it's compile time in any case. It's a static assert. So it's compile time in any case. But surprise. It failed on the static assert. So as I mentioned, there are rules. When you're writing a require expression, what you write inside the require expression itself will not be executed. You're just saying here, please tell me if this operation is permitted. That's it. And of course it's permitted to use same as on T and U. You can use same as on anything. We are not actually instantiating it. It doesn't return a type. It doesn't do anything. So the concept, the require itself, it's satisfied. Everything works, but then it fails. So be careful when you do those things. What you need to do is this simple fix. You just need to add requires inside the require expression. So now when we say on line 159, requires same as T and U, it's not only please tell me if it's something that is permitted, it says please instantiate it and give me the actual answer. Is it true or is it false? And now when we try to run it, it fails on the constraint. Another thing that you can do inside the require expression is checking if types are actually available. So the first line in line 198, you're asking, is this type something that really exists? And in line 199, you're asking, is SC with brackets T exist? Only if those two types do exist, this will be satisfied. And again, because we are in C++, we have many, many ways to do the same thing. So if you really want to be an evil person, you will do an ad hoc require expression on your friends. And that's just like the require clause, the trailing require clause, but it's a require expression. And to do it, you need to write requires. Someone was really cheap. Chris, why not another keyword?
Keywords are very expensive and complicated to get added. It's easier to overload something.
So requires everyone. So requires, you have a parameter, and this requires just says, if I can operate not on this type, please satisfy this requires. So this struct, not oper possible type only, will work only if the type that is provided can be operated with not.
It also has to do with nested parsing of the requires clauses. One clause is entirely separate from the outer requires.
That's true. And this is something just for you to write on your code basis whenever you want to do it, because people will love it. Every requires disjunction can be written as an ad hoc requires. So we can just say if we want something to be or not, we can just do requires, stud is pointer v, requires, std convertible to in, requires, and then you have a lot of smiles because your coworkers will smile with you. Now, for the usage itself, here we have a concept that we already seen. It says that if it's something that is not equal, and it must be convertible, the return must be convertible to bool. How do we use it? Again, there are many different ways to use a concept. The first way is to use it inside the template itself. So here you can see we are defining type name end iterator. Then we want the begin iterator to be not equable to the end iterator. And as I mentioned, the first parameter will be deduced from BI itself. So actually what is written inside there is nec on BI.ei. And then you have a function for fun with BI and EI, and it will be called if and only if EI and BI can be not equal. Another way to do it is with a trailing requires after the after the template itself. As we've seen before, we have the template, we have BI and AI, and we're saying it requires not equal on BI AI, and then almost the same thing. Another way to do it is to require a function to do something. So it's a trailing require after function definition. Here we are saying, okay, it's templated. We have this function, but this function requires that BI and AI are not equal on. Not equal on those two things should be satisfied. And the last way to do it is to use auto parameters and to use it inside the parameters to the function itself. So we have auto BI, and then we're saying not equal on decal type on BI, auto EI. A little bit more complex to write, but maybe sometimes you will want to use it like this. Each one of this implementation and each one of those usages are good for something else. So you just need to choose what is the most correct way to go for you. Personally, I like to use it inside templates. And if I write a generic lambdas, so I use something like this. And there's an example. We're using a fun with 1 and 1 UL, and that's fine. And now we're using fun with 1 and stud vector of int of 1, and we're getting what you asked. Because 1 and the vector cannot commence the operator not equal, it will be invalid. But the thing is, it's really nice because the error messages are very clear. Because BI not equal EI would be invalid, invalid operand to binary operator expression, int and stud vector. That's nice. Okay. This is an example of how to write a function that checks that all values are integral. Stud conjunction is something that was introduced in C++17, and it says all the type traits inside me must be valid. It just does AND between all of those things and takes the value from them by themselves. My question is it a good way to write something like that in C++20? Basically, it requires, will do, you had an answer?
I was wondering if you could use fold expressions, or maybe not better.
No, it is better, but it's going to be on the next slide. So yeah, fold expression. But here, the thing is, this will work. So if we will use it with check integrals with 1 UL, and a double type, it will tell us, okay, it's not satisfied. The require is not satisfied, but why is it not satisfied? It's not satisfied because stud conjunction is not satisfied. Is it helpful? Not really. The right way to do it is to use fold expression, as Wessam said. And why it's good to use it? Because every concept in the standard, or every concept that you write, have a phase that's called normalization phase. During the normalization phase, all the things that you've written in the concept are converted to atomic Boolean expressions. And those atomic Boolean expressions are evaluated one after another. So this is really helpful, not just for this, we will see the error message in a second, but it is helpful for overloading. So you can have something that is more concrete and less concrete, and then it's very helpful for you if you need something overloaded on something that is more concrete or less concrete to the types and the things that you need to do. And now, if we will call check integral function with 1, 2, and double, we will get, okay, it's not satisfied, but why is it not satisfied? Because double does not satisfy integral. So now it's understandable. Now we know what the problem is, not just that conjunction didn't work. And now let's get to the is container. Now we will develop the is container that we developed in C++17. We will develop it with C++20, and we will create all the concepts that we need for it. So not equal begin and end. It's a require expression that gets a container parameter into it. And then we have a compound expression inside it that says, if std begin not equal std end, and the return time is the same as bool, then it will be satisfied. The other concept is called has begin and end. So it's a very simple one that says it has to use, if the parameter that is provided to this expression can be called with std begin and can be called with std end, that will be satisfied. Incrementable begin, again, a require expression, it will be satisfied in an if and only if std begin on C can be incremented. The referenceable begin, not void. So you remember what we had to do with type traits, all this thing with constant expression and nuts and everything. Here we can do it in one line. We can just say, this is a require expression. Inside it, it requires that the decal type of the reference from the begin, if you use it with C, is not equal, is not the same as bool. And sorry, it's the same as void, not. So it's not the same as void. You can dereference it. You will check what the return type is. If it's not void, it will be satisfied. The last thing that we will need to do is to create this concept, begin and add copy constructible and destructible. It requires to get another container type. It uses the require expression, and it just uses four standard concepts inside it: copy constructible and destructible on std begin and std end, and that's it. Now to the main concept itself. So we have a concept that's called container, and it's calling has begin and incrementable begin, and dereferenceable begin not void, and begin and copy constructible and destructible. That's it. We don't have all these things that we had to do before to extract types, to use decal type values, to use decal type types, to do all those metaprogramming or generic programming things. We are just writing code. Simple code that most people will understand. And how to use it. The usage example is really, really simple. So there's a function that's called is first element the same. And here we are saying we want those two parameters to this function to be containers. I don't care which container it is. It can be a map, it can be a list, it can be whatever you want. It just has to be a std container. If we know that C1 and C2 is a std container, we already know, because it was satisfied, the concept was satisfied, we know that we can dereference and we can call std begin on them. So all we need to do here, if we're actually getting inside the function and we're actually receiving two things that are std containers, we can dereference them and we can use the equal operator between those two things. As simple as that. And here's an example with std vector and std array. We are calling this function with v and a, and that's fine, no problem here. But if we will try to call it with something that is a tuple is not a container, doesn't obey all the rules that container have. If we will call the same thing with a tuple, we will get this message that there is no function that can be called. Why it can't be called? Because tuple does not satisfy has begin and end. Again, readable errors. That's something else for C++. So concept simplify your code. Thank you. Concept simplify your code. Concept make your life much, much easier. But with great power comes great responsibility. So you can do a lot of things, but because it's so simple to do these things, you may do it incorrectly. I showed a couple of these things during the talk, like the require inside the requires. If you're not familiar with it, you may just say, okay, I've written something and it should be okay, and then you think it's constrained and it's not. And then you will have bugs that you haven't thought about, but I use a concept. They told me concept will work. You have to be careful. You have to learn all the things. C++ as a language is a language that makes you learn things. And if you don't know how to use it exactly, you should learn. Because the errors that you will introduce will be horrible. Makes metaprogramming easier. That's the most important thing for me. So as a metaprogramming enthusiast, and a person that tries to explain to people that not to be afraid of this thing, it's not a boogeyman. You can do a lot of amazing things with those things, with metaprogramming. It's really important and it's really nice that now we have something that people can read and maintain. But then I return again to the thing, if too much people will maintain it and they don't know what they're doing, it's much easier to break things. So be careful. Make compiler errors much cleaner. Yes. Enable if error messages in newer compilers are clear as well. It's worth mentioning. So if you can move to a newer compiler, do it. And just let's watch. That's the difference between the first concept and the second concept. Most people, I guess, won't even want to read this one, right? They will look at it and say, no, that's it. I'm done. But the other one, it's readable, right? You understand exactly what you want from here. So which one would you use? No one. Neither. I don't want it in my code base. Good question. There's a small overhead when you use concepts. So traits are faster, but not by a lot. And with the safety and the slickness of concepts, in my opinion, it's something it's worth paying for. And I'm working with something that accelerates things. So every microsecond for me is important, even when I'm compiling, because compilation for me is part of the process. And I'm willing to pay that.
Because usually it will be in a file, it will be included everywhere, and every compilation will be.
Same with templates. It's the same with templates. It's adds everywhere, but it's very small. You will not actually, if you don't have, well, I have templates everywhere. So my code generation library is template based. It's metaprogramming like crazy. It's metaprogramming like crazy, and we are using concept almost everywhere. And we started with C++17. Now we're using C++20. There's almost no difference in compile time. And yet, I know there is an overhead. So as the robot says here, it's 83.6% readable. In my opinion, we still have a way to go here. It's not perfect, but it's much better than it was before. Basically, I've finished what I had to say about concepts and all the things that we can do with them. But I have prepared bonus pop quiz for you metaprogramming lovers. So because we finished a little bit early, do I have 5 minutes? So because we finished a little bit early, there's a pop quiz. We have something like this. We have a res type that is just a template class, a struct, that has nothing inside it. We have a specialization of the same class with R and arguments. And in line 7, we are using R type. And then we have a function that receives this funky code that does something. Can someone think about what foo does? Anyone? Chris? René? No?
Isn't deducing the actual type for a member function is deducing the argument types and the type?
Yes. So, can you remind me your name again? I'm sorry. But Vincent? So what Vincent is saying, basically what it does here, it detects the return type for a member function without providing arguments. So it's pretty neat, right? And that's how you use it. So for example, if we have struct X and struct Y, each one of them has an add function. One receives 2 integers and returns an int. One receives a double and returns a double. When I wrote these slides for CPP now, it was before we knew all the traits and everything, so I implemented my own is same here, but it's not important. And then all you need to do is to call isSame with decal type with foo and provide the member function to it. And then you can say, is it an integer or is it a double? Easy as that. Really simple. That's why I love this generic and metaprogramming. You can do things with it that are very, very powerful. And let's digest it a little bit. So we have a res type. As I said, one of those is a specialization of the other. R is a return type. Args are a variadic template of arguments that we're receiving. And the specialization said, if res is instantiated for a function, then we will use the R type. Then foo function itself, it's templated on M and T. M is the actual function signature. T, pointer, is because that's the way that we write pointers to member functions. And then if and only if we have a resolution type from here, this will be called. If not, we will have Sfine. There's actually a slicker way to do it with C++, stud function. Stud function usually has an overhead for usage, but here we're not actually using it. We're just taking something from it, and they already implemented the same concept for us. So we just need to implement the foo function and use the stud function result type. And that's it. So now I have to go back and say thank you, and do you have any questions?